I want to talk about some historical applications of trigonometry and a little geometry. It's pretty impressive what the ancient Greeks were able to do before they had a telescope or other modern measuring devices, GPS and all sorts of things. They are not exactly accurate, but they are amazingly close. The first one I want to talk to you about is Eratosthenes' calculation of the circumference of the Earth, which took place in about 240 BC. Just as an interesting side note, in the Middle Ages, many people thought the world was flat, but long before that, the Greeks knew that the Earth was round. Somehow, in the fall of the Roman Empire, a lot of the Greek mathematical knowledge was lost to the Western world and ended up in India and other Eastern countries. And then when trade routes reopened towards the end of the Middle Ages, that knowledge came back to Western Europe and inspired the Renaissance. But at this point, early on in ancient Greece, they knew the world was round. So here, let me explain what this picture represents. Known information. Now, this didn't take place all on one day that some Greeks said, hey, let's measure the circumference of the Earth. This had to happen over a long period of time where certain things were noticed and measured and planned out here. But someone noticed that at a place called Syene, when the sun was directly overhead at the summer solstice, the sun shone directly down a well because you could see the sun reflecting off the water at the bottom of this deep well, and it only happened on that one particular day. So a very observant Greek person decided, though, the sun must be coming in directly perpendicular to the surface of the Earth right there. Now, on the same day, on the day of the summer solstice in Alexandria, the sun cast an angle, a shadow, at an obelisk that they were able to figure out that this angle was 7.5 degrees. So the rays of the sun were coming in at a 7.5 degree angle at Alexandria the same day they were coming in at basically 0 degrees in Syene. Another known fact was that the distance between Syene and Alexandria is 500 miles. So we're going to use this information to calculate the circumference of the Earth, just using a little basic geometry and a proportion. So first of all, we know that because we have parallel lines cut by a transversal, this angle 7.5 is repeated down here. So this angle here is also 7.5, and I am writing with my cursor, so hopefully that's actually not too bad. Now let's look at how the work is set up. Notice that we have a section, 7.5, of the entire degrees of the circle. There's 360 degrees in a circle, and this is one little segment of it. This segment cuts an arc, this angle cuts an arc that's 500 miles, and that arc is a segment of the entire circumference. So we can set up a ratio where we have a part to a whole. It looks like this. Okay, so 7.5 is to 360 as 500 miles is to the entire circumference. So let's look at how we would solve this. Okay, so we have here cross multiplying c times 7.5 is 360 times 500. Divide both sides by 7.5, and you end up with a circumference of 24,000 miles. The actual circumference of the Earth is 24,901 miles, so that's pretty darn close. Using the Greeks' measurement of the circumference, they also knew enough geometry to know that the circumference was 2 pi times the radius. They may not have used the number pi as we use it, as that long, non-repeating, non-terminating decimal, but they had a pretty good approximation for pi back then. So if we divide 24,000 by 2 pi, we get the radius. And for convenience for computation later on, I'm going to round that to 3,820 miles. That's not as close to the actual one as the circumference is, because the Earth is not a perfect sphere. The actual radius turns out to be 3,944 miles, but we're going to go ahead and use the Greeks' approximation for our historical problems. Now, to add more amazement to the situation, the Greeks are going to actually compute quite accurately the distance to the moon just by someone standing and looking at the moon on the surface of the Earth, actually from 2 different spots. So first of all, let's look at some given information. The distance to the moon that we're calculating is this distance PM, or we're also going to call it x. We know the radius of the Earth from the previous problem, so I'm going to label those two as 3820. And this angle right here, theta, is known to be 89 degrees and 4 minutes. A minute is 1/60th of a degree, so we can write that as 89 plus 4/60th degree. Now the way this angle was calculated was by knowing the distance between points A and B and P on the Earth. So once again, this was not done in a day or two. Someone had to actually figure out the distance between these 2 points. And the moon had to be observed on the same day at each of those 2 points to have an accurate reading here. So point A, the point at which the moon is just visible at the horizon, that allows us to make this a tangent line to the circle, so the radius is perpendicular to the tangent line of the circle, and this gives us a right angle, which we need. So you're looking out, and basically the moon is just rising, okay? Or just setting, depending which direction you're looking, I guess. Then this point right here is a point at which the moon is directly overhead. So you're looking straight up at the moon from this point. And the angle in between these 2 points on the Earth is computed to be 89 degrees and 4 minutes based on this being a section of an arc of the circle and that same proportion that we did before in problem number 1. So we have now a right triangle. We have this angle. This radius here is adjacent to this angle, and this whole distance from E all the way to M is the hypotenuse of the right triangle. So the hypotenuse is actually 3,820 plus x. So when we set up our ratio, it's cosine of 89 plus 4/60 degrees equals 3,820 divided by 3,820 plus x. So going through the work here, we have, I got the decimal approximation with this. Now I'm multiplying both sides by the denominator. Then I'm going to divide both sides by this cosine value. And finally I'm going to subtract 3,820 from both sides. So this is what I end up with. And when I put this in the calculator, I end up with 230,694 miles. It turns out, and I've got some numbers down here to show you some actual distances, it turns out that the actual distance to the moon is 238,857 miles, which is only about an 8,000 mile difference. Now you might think 8,000 miles is a pretty big difference, but when you're looking at the whole distance here of 238,857, if you calculate a percent error by taking the actual distance minus the distance we calculated divided by the actual distance, it turns out to be only a 3.4% error, which is a pretty small error considering the crudity of their measurements. It's pretty amazing how accurate they were with just some very clever observations and a little bit of basic trigonometry and geometry. So be impressed with what the Greeks accomplished here. And those are my examples. There's a couple other historical problems that I'll be giving you for homework.